Hello, everyone. Welcome to the webinar series introducing the Ocean Ice Project. My name is Eva Hročáková and I work at the European Polar Board that is facilitating this webinar series. For those of you who still don't know the Ocean Ice Project, it's a Horizon Europe project funded by the EU Commission and the UK Research and Innovation. And the acronym of Ocean Ice stands for Ocean Cryosphere Exchanges in Antarctica, Impacts on Climate and the Earth System. I will not go into details now, but if you are interested in learning more, you are always welcome to visit Ocean Ice website. I will put a link in the chat. And as you probably already know, each of the webinars in this series is dedicated to some of the work packages or subdivisions of the project. All the work packages are different. Each of them has a specific goal, like a chapter in the book, with its own tasks, team, and timeline. In the last webinar, we talked about the data management. In today's webinar, we will focus on different work package 4, that is dedicated to quantification of Antarctic ice sheet, deep uncertainty, and freshwater fluxes under climate forcing, which is actually one of the key focuses of the project. So it's my big pleasure to welcome today's experts who will tell you more. And it's Jan de Rydt, Vio Coulon, Qing, and Frank Pattyn. Their presentations will be followed by Q&A. And I would also like to remind you that all webinars are being recorded and can be found on the EPB and Ocean Ice YouTube channel afterwards. I will also put a link to the YouTube channel in the chat. Thank you so much. And now I give a word to Jan.
Great, thank you very much, Eva. Good morning, everyone. From myself, my name is Jan de Rydt. I'm an ice and ocean modeler at Northumbria University in the UK. I'm gonna start sharing my screen here. We have prepared some slides for you this morning. So as Eva mentioned, we will be introducing the work of work package 4, which is on the quantification of Antarctic ice sheet deep uncertainty and freshwater fluxes under climate forcing. The work package is rather small in the numbers of people. We are 4 people, Frank and Vio at the Université Libre de Bruxelles, ice sheet modelers, and it's myself and Qing at Northumbria University in Newcastle, also ice sheet modelers. And the nice thing is that because we're so small, you get a chance to hear from all of us today. So we will present our work. I will start off with a short introduction, the motivation for our work and the science context. Then Vio and Qin will present some of their ongoing work, some of the results that we have already obtained within work package 4. And then Frank will close by highlighting some of the linkages with and synergies with other work within the broader Ocean Ice project. So let's get started. Just to orient yourself as to where we fit within Ocean Ice, this is the project overview. And I would like you to focus on the left-hand side here, this big box. These are all the scientific work packages. And there are 6 of them, and they can be broadly categorized into 3 work packages, 1 to 3, which focus on polar processes, so essentially the physics, and they're very oriented towards observations and integrating models with observations. And then there are work packages 4, 5, and 6, which are focused on the impacts, in particular the ice sheet impacts on the ocean, and on the global climate. And work package 4 sits within this second category, and our focus is on the Antarctic ice sheet and ongoing and future changes in the ice sheet, and then linking to the the global impacts of those changes. So, as we all know, both the Antarctic and the Greenland ice sheet have been observed to lose mass, and the videos that you see here are from the GRACE satellite, and they indicate how much and where these ice sheets are losing mass. In Antarctica, the focus is on the West Antarctic ice sheet, so I don't know if you can see my cursor, but in this region here, where the ice sheet has been observed to lose mass as an accelerating rate. And the synthesis of the scientific community at present looks as follows. There's the curves on the right-hand side showing over the last 3 decades the mass change relative to the 1990s. And there are a few things I would like to highlight on this graph. First of all, in blue is the Greenland ice sheet, is the biggest contributor present day to mass loss. And then in pink or purple is the Antarctic ice sheet. And most of that loss comes from the West Antarctic ice sheet, which is shown in green. And the other thing to notice is that these curves show an accelerating trend. So the mass loss is increasing over time. And in total, the Antarctic ice sheet has contributed about 8 millimeters of sea level rise since the early 1990s. Now, the question is always, how will this trend continue in the future? And these are the results that the IPCC report AR6 presented in 2021, based on a number of modeling studies projecting forward this increasing trend in mass loss. And as you can see, the projected trends strongly depend on the climate scenario. And the contribution to sea level rise from the Antarctic ice sheet can be anywhere between 0.5 meter and 1 meter, depending on the scenario. Then that's relative to 1900. With, of course, some significant uncertainties associated with those projections. Now, sea level rise is not the only concern when we think about changes in the ice sheets. In particular for Antarctica, the way that the ice sheet interacts with the rest of the climate system happens through other processes as well. And these global impacts also remain somewhat uncertain. What I show here is a result from a study that was conducted in 2018, whereby the authors increased the amount of fresh water that was released from the Antarctic ice sheet into the ocean and looked at the impacts, the global impacts of that in numerical ocean simulations. And what they found was that when they increased the freshwater discharge of the ice sheet into the ocean, there were global repercussions for the ocean state. On the left-hand side shows the surface temperature trends. In general, the surface warming is reduced, hence the blue colors. And on the right-hand side, coincides with that surface slowing, is a warming of the deep waters. And that could have feedbacks on the ice sheet. As the deeper waters are allowed to warm, ice shelves are allowed to melt more, and more fresh water is allowed to enter into the oceans. Now, there are some remarks or side notes to be made about this and similar studies, in that the way the freshwater fluxes are represented in these models is not necessarily in agreement with the way the freshwater fluxes enter into the ocean in the real system. And what I mean is that when they do these so-called hosing experiments where they increase the flux into the ocean, they do this by means of a flux at the surface and distribute it in some uniform way all around Antarctica. Now we know that the system is rather more complex than that. And so if we look at the Antarctic ice sheet, there are really three different sources of freshwater fluxes that we should distinguish. The first one is iceberg calving, so fresh water that gets released in solid form and that can travel at the surface of the ocean for quite some distance before these icebergs melt and the fresh water gets released, not necessarily right next to the ice sheet. The other form of fresh water is through subshelf melting, and in this case, some of that fresh water can be released at depth, so not necessarily at the surface. And then the third form, which is currently rather small in Antarctica, but can increase in the future, is what we call surface runoff. That means melting of ice at the surface that runs off over the surface of the ice sheet and then ends up in the ocean at the surface level. So these three different forms of freshwater fluxes each enter into the ocean in a different way. However, most of the CMIP class coupled models represent the ice sheet in a rather simplified way, and it looks a little bit like this schematic. So what they assume is that Antarctica is essentially just a big glacier sitting on rock above sea level, and whatever snow falls in the interior immediately runs off in liquid form at the surface into the ocean. And so to marry this picture from the previous slide, this here, with what models tend to do present day is essentially the aim of Work Package 4 in Ocean Ice. So what we aim to do is produce projections of each of these different forms of freshwater from ice sheet models, and then provide these as data sets to Earth system modelers who are then able to implement these fluxes in the correct form at the correct places around Antarctica as hosing into the ocean. So just to summarize, the aims of Work Package 4 are to project the freshwater fluxes of the Antarctic ice sheet. And we will also do this in a coupled ice-ocean model format. Today, however, we will focus only on the standalone ice sheet simulations. Then, to provide spatial and temporal trends in each of these forms of freshwater, which is calving of icebergs, its basal melt of the ice shelves, and its surface runoff from the Antarctic basins, between present day and 2300 for a number of climate scenarios. And then with that, to quantify the uncertainties that come from either uncertain physics in our ice sheet models or uncertainties in the future forcing scenarios. So we've made quite a lot of progress towards these aims, towards these goals. And so for the rest of the seminar, I'm going to leave the floor to Vio and Qing to tell us a little bit more about what we have been doing, how we have been approaching these problems, and the data sets that we have. So with that, I'll stop sharing here, and I'll hand over to you, Vio.
Thank you. Good morning, everyone. So let me share my screen. All right. So yes, so as Jan just nicely explained, so there's the need to account for the effects of future freshwater discharge from the Antarctic ice sheet in climate projections. But most climate models lack interactive ice sheets and hence are not able to account for future spatiotemporal trends in Antarctic freshwater discharge. And so To address this, here we present some projections, some historically calibrated projections of iceberg calving, surface runoff, and subshelf melting from the Antarctic ice sheets to the year 2300. And so those projections are provided with quantified uncertainties and for 27 drainage basins from the Antarctic ice sheet. And so as Jan just explained, the idea is that those projections could be used to force climate models lacking interactive ice sheets, and hence enabling them to approximate future spatiotemporal trends in Antarctic freshwater discharge. And so the projections that I present here were derived from an ensemble of standalone ice sheet model projections performed with the ice sheet model Coulon. And those simulations were forced by oceanic and atmospheric projections from 4 CMIP6 climate models under both the low emission SSP126 and the very high emission SSP585 scenarios. And so in this standalone ice sheet model framework, subshelf melting and iceberg calving here are calculated by parameterizations. And similarly, the surface runoff is calculated by a positive degree day scheme. And so overall, the projections that we show here are derived from an ensemble of 240 members of ice sheet model simulations, which covers and samples uncertainties in both ice climate interactions and ice dynamics. And so, for example, so the uncertainties that we take into account are summarized in this table here. And so we use a panel of existing subshelf melt parameterizations. So for each, we vary a key parameter which modulates the sensitivity of the subshelf melting to the ocean thermal forcing. Similarly, we also use different existing calving laws and vary also a sensitive parameter for each. In terms of ice dynamics, we cover different spatial resolutions of the ice sheet model. We also vary parameters from our positive degree day scheme, which influence the magnitude of the surface runoff, and so on. And also our simulations begin in the past, in 1990, and this allows us to calibrate them, so to calibrate our ensemble by comparing model results over the past decades with regional mass balance estimates from the latest INBI assessment. And so this means that we attribute a higher predictive weight within the ensemble to simulations that better reproduce the observations. And so you see that by applying such a Bayesian framework, this allows us to reduce the spread within the ensemble, and so to have a calibrated ensemble which reproduces the observations in quite good, the historical trends are in quite good agreement with the observations. So now in terms of freshwater fluxes, so we see here that our calibrated ensemble reproduces on average over the historical periods a total freshwater discharge from the Antarctic ice sheets of a bit more than 3,000 gigatons per year. And we see here on this pie chart that the majority of this discharge occurs in the solid form through iceberg calving, while subshelf melting accounts for roughly 40%, and surface runoff is almost negligible and accounts for less than 1%. And we also have a look at the spatial distribution of these freshwater exports around the ice sheet by aggregating our basin estimates into 5 distinct ocean regions, which are shown on the figure here. And we see that iceberg calving is the dominant freshwater source for all of those regions, but the Amundsen Sea, where subshelf melting accounts for a bit more than 60%. And so also to validate those freshwater flux hindcasts, we compare them here on the figure with some observational estimates from Davis and et al., which are shown in red. And we see overall that our hindcasts agree fairly well with those observations, both in terms of magnitude and partitioning between the subshelf melting and the iceberg calving. So now we can have a look into the future with our projections of here, so subshelf melting in red, iceberg calving in yellow, and surface runoff in blue, which are here aggregated over the whole ice sheets to the year 2300, and there are two emission scenarios. And so what we can see, first of all, is that under our two scenarios, the iceberg calving is projected to remain fairly constant in time. This is not the case, however, for the subshelf melting, which we see is projected to increase. And again, for our two scenarios, to surpass the initially dominating iceberg calving by around 2050. And so this means that we project for a shift from a mainly solid to mainly liquid freshwater discharge from the ice sheet. And so while under the low emission scenario, the subshelf melting we see is then projected to stabilize, this is not the case under the very high emission scenario, where subshelf melting keeps increasing and reaches magnitude of more than 5 times the present day magnitude by year 2300. And then for the surface runoff, we see that it remains almost negligible under the low emission scenario, but that it increases with the warming air temperatures under the very high emission scenarios, reaching about 10% of the total Antarctic discharge by the end of the century, and similar magnitudes to the subshelf melting by year 2300. And so overall, we project an increase in the total magnitude of the freshwater export from the Antarctic ice sheet of about 20% by year 2300 under the low emission scenario, and by a factor of more than 4 under the very high emission scenario. And so if we have a look again at the regional scale, and so the spatial distribution of this freshwater discharge around the ice sheets, here focusing on the very high emission scenario, for which I've shown we have a strong increase in the magnitude of the discharge which is projected. We see that most of the discharge is projected to occur in West Antarctica, and more specifically in the Amundsen and Weddell seas. And we see also that the storyline I've just told overall holds for all of our regions, with an increase in subshelf melting and later on an increase in surface runoff. And we see that this increase in subshelf melting is particularly pronounced in the Weddell Sea, where fluxes by the end of the century under SSP 585 reach 4 times those of the low emission scenario. So in the case of subshelf melting, changes in the ice shelf draft can cause shifts in the vertical distribution of the freshwater inputs. And so here we show the evolution of the depth profile of the subshelf melting with time. And so the darker the color, the more advanced in time for our 5 oceanic regions. And so we see that overall increasing meltwater is projected to be discharged at greater depth through subshelf melting due to grounding line restraints in the main marine basins of the ice sheets. And so this is especially pronounced in the Amundsen and Ross seas, and also to a lesser extent in the Western Pacific Ocean. And so on those figures, you also see the evolution of the mean grounding line depth with the dotted lines, and the dashed lines show the evolution of the mean ice front drafts. And so we see that the projected thinning of our ice shelves with time leads to a reduction of the ice front draft, and hence a reduction of the iceberg thickness in the coming decades and centuries. All right, so to summarize, we have presented here projections of Antarctic freshwater fluxes that were performed with the ice sheet model Qing. And so these projections are from the year 1990 to the year 2300 under 2 emission scenarios. And so they show potentially large changes in the magnitude and partitioning and spatial distribution of this freshwater export from the Antarctic ice sheet. And so hopefully these projections can be used to force climate models lacking interactive ice sheets and enabling them to account for the impacts of those changes. And so this work was published a few months ago in JRL. And so you have here a QR code which provides you with an access to the paper. So feel free to have a look at it if you want to have more details. And also the data set is freely accessible on Zenodo, thanks to the link here. So yes, so now I will give the floor to Qing for the next steps that were performed in Work Package 4. Thank you very much.
Thank you, Will. Hello, everyone. I'm going to share my screen. Good morning, everyone. I'm going to present my ongoing work about calibration of ice sheet basal melt parameterizations. In the context about climate change, around half of the ice sheet surface mass gain is offset by basal melting, driven by the intrusion of warm ocean water beneath floating ice shelves. This warm ocean water, as known as cyclopolar deep water, CDW, is slightly increased in temperature in recent decades. Associated with the shallower of the upper layer, these processes allow CDW could greater access to the continental shelf. However, no clear long-term trend in basal melt is observed. But given that many Antarctic ice sheet projections shows the high sensitivity to increase the basal melt around many of the ice shelves of the Antarctic, particularly in Western Antarctic. So my ongoing work about transient Heinke simulations for recent 20 years, which starting from a range of initial states, we're focusing on basal melt. Similar with what Will did in her historical period, but I'm using a different ice sheet model, UWA. UWA is a finite element ice flow model. And I'm using a high resolution psycho-Antarctic setup of UWA. Here I show the mesh in my simulations, and the red line is the grounding line of the year 2000. Our ice sheet models needs information from basal melt of ice shelves. We usually rely on basal melt parameterizations to link the ocean properties in front of the ice shelf to basal melt best of the ice shelf. But there are large uncertainties remain in basal melt. And that kind of uncertainty is largely come from different choices of basal melt parameterizations and different choices of key parameters, and also come from the uncertainties of oceanic observations. I use the three of Besselmel parameterizations in my simulations. They are plume model, Pico model, and local quadratic parameterization. I will present plume model here as an example. And the key parameters in plume model is gamma TS, heat and salt exchange coefficient, and E0 entrainment coefficient. And I use the two different oceanic forcing data sets here. The first one is MIP6, and the second one is produced by Shenjie in Ocean Ice Project Work Package 1. Here I show the ambient water temperature here for each of the ice shelf around the Antarctic. And this ambient water temperature is the average temperature under the thermocline depths. Yes, and here I show the difference between these two different oceanic forcing data sets. We can see that for this, the y-axis is average temperature below the thermocline. For the warm cavities, we find that Shenjie's data is warmer than ISMIP6, but for some cold cavities, ISMIP6 have slightly warmer forcing temperature than Work Package 1's data. Sorry, I forgot. So to represent parameter uncertainties in Besselmel processes, we will use a large range of parameter space, but we don't really want to using that unrealistic parameter values in our simulations, because we want to make sure our simulations remain physically meaningful. So the next step is constrain Besselmel parameter priors. To constrain the priors, I run melt rate simulations using a fixed geometry of the year 2000, and then compare the model Besselmel rates results with the satellite observation. Here I firstly bring the Pi Island and Swiss Glacier ice shelf melt rate as an example. This figure shows the melt rates forcing by Work Package 1's dataset and parameterized using the plume model for Pi Island and Swiss ice shelves. In this two-dimensional parameter space, the x-axis is gamma TS and y is E0. So each point in this two-dimensional space means a different combination of gamma TS and E0, and also corresponds to a distinct Besselmel pattern. So for if we choose a large gamma TS and a large E0, we will have a very high melt rate in this right top corner. And if we use a very small value of gamma TS and small value of E0, we will have very low Besselmel rate in this left bottom corner. And this color line, this red line, is a contour line of the average, the mean observational Besselmel rate for this ice shelf. So if I select 2 points along this contour line, which means they have the same simulated total Besselmel rate for Pi Island and Swiss Glacier, but we can see from these two figures, they have very different spatial distribution pattern of Besselmel rate. And if we bring the mean observational basal melt rate for 19 ice shelves around the Antarctic, if we bring all of them here, you can see 19 color lines here. And the color represents the ambient water temperature. So red colors, warm cavities, and blue colors, cold cavities. Then you can see it's very difficult to select a single parameter combination to use in our simulations. So that is why we would like to use a range of choice of values of parameter combinations. And I bring a black box here to define the boundary of the prior parameter space. So all the subsequent sampling is retreated to this physical plausible region. By doing this constraint of priors helps identify parameter combinations that produce basal melting within a realistic range, thereby providing a more reliable representation of ice-ocean interactions in our hindcast simulations. At the same time, we would like to retain a diversity of basal melt patterns that are consistent with observations, since multiple spatial patterns of melting are physical plausible. So next step, after we doing with this transient hindcast simulations for recent 20 years, I will compare the observation change in velocity, ice synchronous, grounding line locations with our simulation results. And after the calibration, we will treat this calibrated set to our transient forecast simulations for the future 300 years. Here I bring an example of the sampling of parameter space for ice and Coulon model parameters. So in this part with the yellow background, there are all ice parameters. And here with green background, there are all Coulon model parameters. That's all for my talk. Thank you, everyone.
Okay, and then finally, we'll go into a cross-cutting team, which is the deep uncertainty team, Freshwater Fluxes. So, Qing, next slide, please. So, yeah, this cross-cutting team already had a logo before the team was even invented. And since beer is for the ocean anyway, a freshwater flux, so that was easily found. So the cross-cutting team is one of the several cross-cutting teams we have in the project that go along different work packages. And so this is not limited to one work package, but involves many of them. And so this is a work package on the deep uncertainty, or this is a cross-cutting team on the deep uncertainty in freshwater fluxes. So first of all, it focuses on freshwater fluxes, and especially the link between observational freshwater fluxes going towards the modeling of them, and then also the coupled, or finally the synergy, the coupled ice-ocean modeling. And then another part of these freshwater fluxes pertains to the deep uncertainty, meaning the low likelihood risks in sea level rise and the low likelihood risks in freshwater fluxes. Next slide, please. So first of all, the synergies, if we look at the how freshwater fluxes are dealt with in different work packages, we have work package 3, which is pertaining to the observation of freshwater fluxes and creating observational data sets of ice sheet mass balance, the forcing and dynamics. So the different components that are present day subshelf melting, present day sub ice melting and its contribution via the basal hydrology to the cavities underneath the ice shelves of the Antarctic ice sheet. Surface runoff, all these factors are related to those data sets, which will be used to validate our ice sheet modeling, which is basically done in this work package 4. But work package 4 is not only producing freshwater fluxes. The work package is a lot, as you have seen in the 2 previous presentations of Vio and Qin, that it is a lot about robust uncertainty quantification. And this is an important aspect of that work package. But then, since we have not only the uncertainty quantification, but therefore also the freshwater fluxes, this is something that feeds into other work packages such as 5 and 6, which are dealing with the modeling. So work package 5 is the ocean modeling, which can use these freshwater fluxes. And instead of using them as, let's say, this global sheet on the ice sheet that is flowing equally everywhere into the ocean, that this is now done in a more robust way, in which we have the different components of freshwater fluxes, liquid, solid, also at the different depths into the oceans in different areas around the Antarctic ice sheet. And this is an impact that we want to study. And then work package 6 is then finally, the impact of this, the whole distribution of freshwater fluxes present and future on the ice sheet, and also the circulation of the Southern Ocean. Next slide, please. And then, of course, we have the aspect of the deep uncertainty. Deep uncertainty is a term that was used already in the special report on oceans and cryosphere of IPCC, and was related to, among others, the uncertainty that we had for some processes that were used in some models. That was especially Mickey, that for which we didn't know much, but such processes could lead to more important sea level increase. So this has also been dealt with to a certain extent within ISMIP 6 by looking at risk-averse scenarios in which at certain moments ice shelves around the Antarctic ice sheet were collapsed. And then looking at the impact of this. Within this project, within our work package 4, for instance, we have been looking, and we are still looking, at the impact of those processes, and especially related to surface and basal hydrology, also damage of ice sheets and ice shelves, and then definitely also calving. These different processes that of which, let's say, that the marine ice cliff instability is related to calving, is related to damage, is related to hydrofracture, in which we will look at such processes, and in this Bayesian framework, evaluate what the risk is on the freshwater fluxes within DUF. So this is an ongoing thing related to work package 4, of course, but that goes much further throughout the whole ocean ice project. And so with that, I conclude. I don't know if Jan wants to say some final words of wisdom after this.
Thank you, Frank. Thanks everyone. I think that was a really nice overview of all the things we've been up to in work package 4, and showing the very close links to what others are doing within ocean ice. And I think that's one of the strengths of having these big collaborations, is you have this first line of connection between all the different aspects of the climate system. So that's great. No, I think, Eva, we can open the floor to questions at this point, I think, right?
Yeah, indeed. And I would also like to thank you for these insightful presentations. They were really interesting. and they not only deepened our understanding of Antarctic ice sheet processes, but also highlighted the urgency and relevance of this research in the context of global climate change. And indeed, we could go to Q&A now, even though I think also many questions that I had were answered already during the presentations. So I would like to encourage all of you in audience to write your questions in the chat or the Q&A box that is at the bottom of the panel. And while you are thinking, I would start with some of the questions. So question for Bio. Do your simulations include the deep uncertainty Frank mentioned, for example, through MIC parameterizations?
Yes, thanks. It's a good question. So we do not include the Mickey process itself. But as Frank mentioned already a little bit, we account in a way for deep uncertainty through ice damage. And so ice damage is the accounting for the influence of fractures in the ice on the viscosity of the ice, and so the way it flows. And so the idea is that the more fractured the ice, the easier it will flow. And so this is one process that we take into account, and especially uncertainty in the magnitude of this process is accounted for in our ensemble of simulations that were performed with Coulon. So this is one of the parameters shown in the table that you see in the slide here. So this was our way to approximate high-end ice sheet mass loss. Yes, I hope that answers the question.
Thank you so much. I have also one question for Jan. As a work package lead, what have been the biggest surprises or challenges in coordinating this work in a work package 4?
The hardest thing has been that there's 3 Belgians in this work package and they never agree. No, that's not true. So the biggest surprise is, I mean, when you start this work, I think people had always been focused, at least from the ice sheet modeling point of view, on the total mass loss from these ice sheets, which translate into estimates of sea level rise, which is hugely important, right? This is really a big question that we need to find answers to. But the different approach within Ocean Ice and Work Package 4 to not only focus on the sea level rise, but also learn something about the way that these freshwater fluxes, the mass loss, is partitioned between the different processes, i.e. calving, runoff, and so on, I think has really opened up a different set of discussions and questions between ice sheet modelers and oceanographers, and between ice sheet modelers and people studying the atmosphere. And I think it's been very nice to be able to have these interactions, because ultimately Antarctica is an integral part of the entire climate system, and there are lots of different feedbacks between the different components of the climate system, which is something that we have now started to sort of unpack. And we've started to foster some of those discussions more between the different approaches in climate modeling. I think that's been a very rewarding process, and I hope it's something that we can continue doing throughout Ocean Ice and beyond. So really not just see the ice sheet as a source of sea level rise, but in addition, think of all the other feedbacks that it might link to in the global climate system. So to me, that's been one of the one of the rewarding and most interesting aspects of working in ocean ice.
Thank you so much. And I see we have more questions from audience. So the first one is, how do you measure the actual amount of liquid freshwater flux under the ice sheet from a monitoring perspective? Is it using gliders? Do you think the current amount of monitoring is sufficient to provide adequate ground truthing data?
Well, I can try to give an answer to that. Yeah, this is not part of our work package, but more from work package 3. So if there are people of work package 3, they could better answer. But you cannot directly estimate by measuring the amount, direct measuring the amount of subglacial water, so underneath the grounded ice sheet. That is available or is moving towards the ocean. You can estimate it using the physics. You can use using the thermodynamics of the ice sheet. You can determine how much melt would occur, and then you can also see, based on routing of that meltwater, how much of that meltwater is actually going to the ocean. Of course, it is a lesser amount or a much lesser amount than compared to the other fluxes that we are studying, compared to, like, for instance, the subshelf melt, which is underneath the ice shelves. And that is just yet another way. So if you are thinking there about gliders, so I suppose that this is related to the ocean. There are measurements that are made, direct measurements, and this can be done by radar using phase-sensitive radar or autonomous PRES to put at the surface, and you can measure year-round. You can measure the change of the thickness of the ice shelf, and also the internal layers from which you can determine the vertical velocity profile. And knowing that this profile should be a straight line in a freely floating or in a floating ice shelf, you can determine the difference with the actual bottom reflector. It gives you the amount of melt that is going on. And this is a very accurate way of measuring in time the amount of melt. So, and this is done at several places in Antarctica. There are other ways to do it in basis of remote sensing by taking the flux divergence of the ice, the rate of change of the surface elevation, and then using just simply the conservation of mass, which leads then to, if you know the surface accumulation rate, then you know what the amount of basal melt is. So I hope that answers that question.
Thank you so much, Frank. We have other question from audience, which is, how or why did you choose the levels of SSP used in the two scenarios?
I can try to give an answer to that. So our goal was to produce freshwater flux projections to the year 2300. And so it was not so much of a choice here, in the sense that there are not many other scenarios available to the year 2300. And so we used then what was available from CMIP6 climate models. So there are intermediate SSP scenarios that are available to the year 2100. But beyond that, we had to stick to the low and very high emission scenarios, unfortunately.
Thank you, Vio. Other question from audience. When Antarctic snowfall increases due to global warming, will there be more Antarctic ice or more melting?
So I think that I can also give an answer to this one. So indeed, we see that we have within a warming climate an increase in those two competing processes. So more snow accumulation and also more surface melting and hence surface runoff. And so what we find, if we have a look at the very high emission scenario, for example, is that on first we have the signal of the increasing snow accumulation which dominates, and so that will compensate the ice loss, for example, through subshelf melting. But then once you pass a given threshold of the atmospheric warming around the ice sheet, and so we estimate this threshold to be around 7.5 degrees of surface warming averaged over around Antarctica. Then beyond this threshold, it is the subshelf melting which takes over and so reduces the compensating effect of the snow accumulation.
Thank you again, Vio. Next question from Francisca Sangiori. I'm a paleoceanographer, and we are trying to reconstruct sea ice in the past, as we think sea ice is important component. What is the role of sea ice incorporated in your modeling study, and is it important at all? Also, we can reconstruct meltwater phases, but the amount of flux is hard to reconstruct, and I guess that would be important as well.
Maybe I can try to answer this. Thank you, Francesca. So these are the simulations that you saw results of today are from ice sheet models, and they do not by default include sea ice. So the ice that we talk about is either grounded on the Antarctic continent or the floating ice shelves, which abut the grounded ice. So from the modeling point of view, what we've presented, there's no interaction with the sea ice. Now, if you think about the physics, I can see two ways in which the sea ice might interact with the Antarctic ice sheet. One could be through some amount of buttressing, which is sometimes an effect we see in Greenland, in the fjords, right? Where you have a melange which then buttresses the upstream grounded ice. Something similar might happen in the future in Antarctica if we have a lot of icebergs that get pushed into narrow embayments. This could actually have a mechanical effect on the ice sheet, but that is not something that we have included in our simulations. And then the other effect is obviously through the ocean and the thermohaline properties of the ocean, right? So as you will know, sea ice has an important contribution to the ocean properties and the dynamics through the circulation, through the formation of bottom water. And again, these are not interactions that we include in our simulation simply because we don't have that interaction with the ocean. It's very much a one-way coupling, right? We take ocean properties from the CMIP climate models, and we put that into our ice sheet model to simulate the ocean properties that then lead to the subshelf melt. But we do not feed back the information into those climate models. And that's sort of the next step, right? When we produce these freshwater fluxes, we really want to understand how it then impacts on the oceanography, and in turn, how it impacts on the sea ice. In principle, only a fully coupled Earth system model can capture that two-way feedback in full. This is sort of the first step to try and understand these connections between sea ice and the Antarctic ice sheet.
Thank you very much, Jan. I don't see any more questions from audience, but maybe I have one more, maybe last question. I'm working as a communications officer, so I have a bit different question for you, less technical, but very important maybe. So I would like to ask you, if you should send one message to general public or people who are not scientists or policymakers, how would you shortly explain why is your work in the project or specifically work in the work package 4 important? Anyone who wants to answer?
Frank, you want to take this one?
I was thinking of you to take it. It's a very important question. It's also a very difficult question. Well, we are in a step of improving things. I mean, sea level is obvious an important societal question, and knowing how, when, and where ice is lost is of course important for any policymaker. Now, what we are focusing on is to look at the interaction of the mass loss, because normally what you see here in the figure that Jan put up, this is just based on ice loss and ocean expansion and all the processes, those basic processes that lead to sea level change. We want to look more closely into the interactions between the ice and the ocean, which are important, because they can work in two ways. They can lead to a negative feedback or a positive feedback. Now, a positive feedback means that the impact of ice, of melting ice on the ocean will lead to, for instance, even more melting of the ice sheet. So that exaggerates or invigorates the amount of melting. If it were a negative impact, then it would counteract it basically. But we know from some coupled experiments that have already been done in the past that if you have more freshwater fluxes from the ice sheet, it may lead in these subshelf cavities to stratification, which may lead in turn to more ice melt. And then there are also another part of this is the way we think of the Antarctic ice sheet as being something that is sitting there far away from us. It may also influence other parts through the ocean. The ocean is an important component, and I'm definitely not the ocean specialist. That's why I was looking at Jan. So that you have so many teleconnections that may play between the northern part and the southern hemisphere, and these teleconnections, because of different amounts of meltwater, of different periods in which this meltwater is host, may play a role. So it's like, yeah, we are in improving, trying to improve those projections of sea level, and by taking into account now the interaction between the ice and the ocean, which is not well represented by now. Jan?
Yeah, thank you very much, Frank. I fully agree. The other thing that is obviously very important and that you touched upon towards the end is those low likelihood, high impact scenarios that will potentially affect a lot of people worldwide, not just in terms of sea level, but also those teleconnections through the ocean and the atmosphere and influencing the global climate. And we feel as ice sheet modelers that there's a very important role for numerical simulations of the ice sheets to try and narrow down at least what that might look like and to how much freshwater additional freshwater that might lead to, and at what timescales. And that is a very difficult question to address, but it is something that we are continuously working towards. So when you think of the distribution, on this slide that you see on your screen, each of those scenarios have a median, but there is also a certain distribution around that median, which expresses the uncertainty that there is. Some of these, and especially the dashed line, those would possibly be very unlikely, but would have a major impact on the climate system. And it's in particularly those that policymakers are very interested in, because to plan for that is a very difficult exercise. And so it's those kind of projections like the dashed line that we are very much focusing on going forward, and that we are trying to improve our tools, our models, our understanding of the physics and the processes that could lead to such a low likelihood but high impact scenario.
Thank you, Jan. I don't see any more questions, so I think we can slowly conclude this webinar. But before we do so, I would also like to share my screen, and I would like to remind you of the next webinars. Yeah, as I mentioned, this is a webinar series, which means we have more webinars coming. So please save the date in your calendars. We will have another webinar on 22nd of May, dedicated to work package 1 and 10, about subpolar circulation, heat delivery, and water mass export. And day after, on 23rd of May, we will have a webinar dedicated to work package 2, about cryosphere ocean interaction processes and feedbacks. Again, there will be space for Q&A. So I hope you will be able to join. I will also add the links to the webinars in the chat. You can click on the links and register for the webinars, which will also save the date for the webinars in your calendars. So please do so. Yeah. Now I would like to thank again to all of you, our today's speakers and experts. I really enjoyed your presentations, and it was very interesting. We also had a high participation today, many nice questions. So I would like to thank to all of you and our audience. Thank you for your interest in the Ocean ICE project. Thank you so much, and I wish you a nice day. Bye, everyone.
Bye.
Everyone.
Bye. Thanks.
Bye.
Bye.
Thank you.